Okay friends, good morning and welcome to this class plate tectonics. So, up to now we are pretty sure that the crustal thickness and the crustal composition, the crustal physical and chemical properties are very much important, because when we are talking about this plate interaction, we will talk about the lithosphere, which mainly composed of the crust as a whole and the upper part of the upper mantle. That is why we are emphasizing on these crustal properties and crustal behavior with respect to temperature, pressure, gravity, composition, thickness and so on. So, today we will confine ourselves in the oceanic crust, because most of this plate tectonic, the oceanic crust is destroyed and the oceanic crust is created, and this continental crust, which was formed from the Archean time, it remains as it is with some modification due to crustal evolution and deformation. However, the oceanic crust, it is newly created at the mid-oceanic ridge and it is recycled at the subduction zone, and finally it is forming a conveyor belt type system. That is why the oceanic crust understanding about its behavior, about its nature and its response to tectonics is very much important. So, the oceanic crust, it is typically 6 to 7 kilometer thick and it lies the average ocean water depth about 4.5 kilometer. So, this 6 to 7 kilometer thick is the average thickness I was talking, but it varies from ocean to ocean, from tectonic setting to tectonic setting. For example, if you talk about this oceanic lithospheric system in the Pacific Ocean, this crustal thickness is somehow different than the Atlantic Ocean. So, on an average it is 6 to 7 kilometer thick, and the thicker oceanic crust occur where the magma supply rate anomalously high due to higher than the normal upper mantle temperature. We know this basaltic magma, which is the chief component of the oceanic crust, which is generated at the mid-oceanic ridge, and the mid-oceanic ridge, it is where this rate of spreading is less compared to the rate of magma eruption. So, there will be accumulation of magma and there will be anomalously thick oceanic crust will be created. And similarly, those area which are characterized by anomalously high upper mantle temperature, that area represents this magmatic eruption and magmatic creation at the upper mantle system. Similarly, there is thinner than normal crust. It forms where this upper mantle temperature is anomalously low, typically because of very low rate of formation. So, here there is an exception, may be exceptionally thick, and there is an exception, may be exceptionally thin, but on an average this oceanic crust thickness, it varies from 6 to 7 kilometer. And very important thing is that this oceanic crust, it is in isostatically balanced with the continental crust in a crustal setting. So, if you see this block diagram here, we have the oceanic crust and this is the ocean water and this is the oceanic crust thickness and this is the continental crust thickness. Now, you imagine the continental crust is thicker as compared to oceanic crust, because if you remember we are talking about this continental crust behavior, the thickness of the continental crust about 40 kilometer. However, compared to that, this oceanic crust thickness is about 6 to 7 kilometer, and it is composed of mainly basalt, and this is granitic to granodiorite and anorthosite like that. So, that means here it is chiefly composed of the silicate minerals, mostly the silicas, and here it is mostly the mafic minerals. So, it is felsic composition, it is mafic composition. So, that is why its density is different. Here this continental crust are less dense as compared to the oceanic crust, which is high density. So, two different density material, they are placed side by side. So, they are putting pressure on the low lying asthenosphere. So, the continental crust being thick, it is putting more pressure compared to this oceanic crust. So, that means if you see here this continental crust, it is putting more pressure, so that the asthenosphere it is going down compared to this asthenospheric situation below this oceanic crust. So, being it thick and it is thin, they are putting certain pressure here and here. However, if you are moving further down and further down, for example, if you see here, if it is moving further down, there is a level at which the pressure created by this continental crust and the pressure created by this oceanic crust remain same, and this level it is called the level of compensation. So, that means below the level of compensation, the pressure exerted by this column of rock and the pressure exerted by this column of rock both are same. So, below that the pressure is considered to be hydrostatic, and above that the pressure is considered to be lithostatic. So, if you remember earlier class, we are talking about this pressure and density of this oceanic crust and the continental crust, where we are talking about the pressure remains constant after the level of compensation. So, this is the level of compensation, below that the pressure increases hydrostatically. So, there would be have to less dense crust at the mountain and high dense crust in the ocean basin. If you see here also, it is 2.7 gram per centimeter cube, however, it is 3 gram per centimeter cube. So, after the level of compensation, the pressure remains constant or it increases at certain rate. So, that is why this continental crust and the oceanic crust, they are lying side by isostatically balanced manner. And the oceanic crust, it is divided into three principal layers. So, what are the three principal layers? The layer 1, it is mostly of sediment. Here you can see this is layer 1, it is sediment. So, here sediment, it is the seabed surface material comprises unconsolidated deposit, including terragenous sediment carried out into deep sea by turbidity current. Along with that, there will be pelagic deposit such as zeolite clays, calcareous and siliceous ooze and manganese nodule. That means, the layer 1, which is composed of sediment, it composed of both the terragenous sediment, which is carried out to this deep ocean basin by the turbidity current from the continental margin to deep ocean basin, and other sediment which is the basin's own sediment, it is precipitate calcium carbonate, precipitate silica, precipitate manganese nodule, precipitate iron nodule, those are basin's own sediment deposited by chemical precipitation. Apart from that, there is some sediment which has biogenic origin, that is the ooze, they are also contributing to that. So, it is a layer which is composed of sediment of different origin. Additional to that, there are certain ocean basins which receive sediment from volcanic origin also. There is volcanic ash, it is falling down. So, volcanoclastic sediments are also there. So, by and large you can say sediments or the layer 1 on the oceanic crust, it is derived from multi source. And here you can see these are some of these photographs, that is the zeolite, then the manganese nodule, then this is the clays, and this is the carbonate sediment above the CCD, and this is the pelagic sediment derived from the organics. So, all these sediments, they are contributing as layer 1 into the ocean basin. Now, the layer 1 is about 0.4 kilometer thick, that is 400 meters thick. However, it varies from place to place. near to the continent, if you see here near to the continent, this layer thickness is more. However, if you are going to this mid-oceanic ridge system, either it is very thin or it is not present. So, though it is about 0.4 kilometer thick, it is the average thickness, and its thickness increases towards the continent and decreases towards the mid-oceanic ridge. Similarly, the input which either this sediment which is near to this continent, it will be of clastic sediment or it will be non-clastic sediment, and that depends upon the depositional environment and the pH of this water. Anyway, the sedimentary thickness varies from continental side to this mid-oceanic ridge side, and it progressively thickens away from the ocean ridge where it is thin or absent. So, it may or may not present here, but if it is present, it is very negligible thing. And there is a systematic variation in the sedimentary thickness from the different oceans and within that ocean at different parts also. For example, it is taken here the Atlantic, Indian Ocean and the Pacifics. So, if you see here, the sedimentary thickness is represented in this relief model. Here you see this area close to India, this is the eastern margin of Indian subcontinent, it is representing high sediment thickness. Similarly, those areas which are here, they are representing the higher sedimentary thickness, and mostly if you notice, mostly the high sedimentary thickness, it is around to the continent, about to the continent. And particularly here you see we have Sundarban delta, we have Krishna Godavari delta, we have Mahanadi delta, all these major rivers are debouching their sediment to the eastern margin. That is why we have more sedimentary input compared to the western margin of Indian subcontinent. Now, compared to this Pacific, Atlantic and Indian Ocean, the sediment thickness vary systematically. For example, this Pacific Ocean is the, you can say, this older one as compared to this Atlantic Ocean. So, it is obvious if it is older, then means the sedimentation is going on for millions of years. So, it should contain thicker sediment compared to the Atlantic. However, the reverse is true. The oceans or this Pacific Ocean, it is surrounded all sides by this trenches, by the subduction zone. So, trenches, that means like this is the subducting system and this is the abducting system, and here is a trench. So, if this continent is here, the sediment is being supplied by or transported by the rivers or anything. So, the sediments are mostly occupied at the trenches rather reaching to this deep ocean basin. So, that is why this periphery of this Pacific Ocean, and it is surrounded by deep trenches, the sediments which are derived from the continents, they are this trench is behaving as a trap to accumulate the sediment here, and that is why less sediment they are reaching deep inside this ocean. So, that is why the sedimentary thickness in the Pacific is less. However, if you compare to the Atlantic here, Atlantic all side it is bounded by the continent, and here if you see all side it is bounded by the continent, and there are major rivers, they are debouching their sediments here. That is why the sedimentary thickness in the continental side or near to the continental side or overall in the Atlantic Ocean is more as compared to the Pacific Ocean. Now, layer 1 is sediment, we all are convinced. Now, coming to the layer 2, which is mostly of volcanic origin, and it is a rugged surface, and mostly it is composed of pillow basalt. Pillow basalt, pillow basalt, you know, when there is basaltic eruption in subaqueous environment, either it is in ocean basin, in the lake, river, or it may be in the permafrost region, this ice sheet. So, there will be sudden cooling, there will be quenching of this upper surface. So, it creates the pillows. These are the pillows of basalt. So, here the layer 1 is sediment, the layer 2 mostly it is composed of pillow basalt. So, that means the basaltic magma, it is originating from here, and once it is erupted here. So, due to this water content of the sediment and this ocean water, it is suddenly quenching and forming some pillows. So, layer 2 is pillows, layer 1 is sediment. So, layer 2, it is of igneous origin. Basalt is olivine thiolite containing calcic plagioclase and are very poor in potassium, sodium and other incompatible element. So, we know this basalt, it is of basalt olivine thiolite. So, this thiolite, it is a kind of basalt, there is a compositional variation from this normal basaltic region, and it is rich in iron and poor in aluminum. So, this thiolitic basalt, it is the typical characteristics of the mid-oceanic ridge basalt, and that is poor in potassium, sodium and other incompatible element. Very little lateral variation in composition except at the volcanic islands. If you see here, these volcanic islands are here. So, these are these hotspot magma derived or formed by the hotspot magma, and this is the ocean ridge basalt. Now, you see the ocean ridge basalt, it is behaving as a carpet, it is lying on the asthenosphere. The basaltic lava carpet, it is on the asthenosphere, which is representing the ocean basin, and the magma is derived from the mantle or this lower part of or the upper part of this mantle. However, if you compare to the hotspot magmatism, the hotspot magmatism, it is coming from D double prime layer, it is around this mantle core boundary. So, now imagine we have a compositional stratigraphy. At one place a magma is derived from this level having certain composition, and another place or the hotspot magma which is derived from this level, it have compositional difference obviously. So, that is why except this is the hotspot magma or the volcanic islands, all other part of this oceanic crust, it is of uniform composition, that is the olivine thiolite, and this layer have a variable thickness, that is from 1 to 2.5 kilometer, and the seismic velocity varies from 3.4 to 6.2 kilometer per second, that we have already discussed here. You see, these are the hotspots, and the hotspot magma is derived from D double prime layer. However, normal oceanic crust, to form normal oceanic crust, this asthenospheric magma, it is deriving here at the mid-oceanic ridge. So, that means two different levels the magmas are deriving. So, that is why it will be of different composition compared to this. That is why there is a variation at the oceanic islands. Now, this layer 2, it is again divided into 3 sublayers. What are those sublayers? The layer 2A, it present only near the oceanic ridge, and where the hydrothermal circulation of seawater occurs. Its thickness is about 0 to 1 kilometer, and it is porous, that is 30 to 50% porosity, and it is rubbly nature and hence allow water to circulate. Now, if you concentrate yourself here, you see at the mid-oceanic ridge system we have different faults, inward facing fault, or it may be inward and outward facing faults. So, either of this case, so these faults allowing water to percolate. Apart from that, we have this pillow basalt, and the pillow basalt, they are highly porous. There are high porosity and permeability among the different pillows. So, that is why anyway it is allowing the water to percolate down. So, this area is porous and permeable, so allowing this water to percolate down. Now, this represents layer 2A. Now, away from that, it is layer 2B, which is formed by the filling of the porosity of the 2A by secondary minerals such as calcite, quartz and zeolite. Now, if you are going away from this mid-oceanic ridge, gradually we are going away from this hot environment, hot magmatic environment. So, that means we are allowing the secondary minerals to precipitate. We have already porosity here, we have faults, we have fractures, and we have pore spaces within that pillows. So, once we are moving away from this system, we are allowing this system to precipitate the secondary minerals. Now, the third layer, that is 2C, it is dominated by intrusives and grades into layer 3. So, that means layer 2A is porous, layer 2B the porosity is filled by secondary minerals, layer 2C it is intruded by the dikes, they are intrusive rocks. So, now if you see here, this is layer 2A, mostly the pillows, you can see the pillows are lying here, and within that pillows there are pore spaces through which water is percolating down. Now, coming here, this is 2B, and the 2B, if you see here, these white colors, they are the secondary minerals, they are filled here, the porosity is filled, you see this is the pillow, and around this pillow these are white color minerals, they are surrounding. Similarly, this is a pillow, and in between this pore space is filled by white color minerals, that is the zeolites or quartz and calcite, like that. Now, this is these two photographs, this is representing 2C, that is the intrusives. So, you can see this within that pillows there are some intrusions, they are the dike intrusions. Here within this pillow there are dike intrusions. So, there is clear cut distinction between this layer 2A, 2B and 2C. Then we are getting to layer 3 of the ocean basin or oceanic crust. So, layer 3 it is nothing, it is the seated dikes, it is the seated dikes. So, if you see here, these are this mantle material, and from which these fractures, they are surrounding fractures, they are supporting this magmatic eruption. So, these are the conduits through which the magma is erupting and forming the pillow basalt at this level. So, the seated dikes are nothing, these are the conduits, these are the fractures which are allowing this magma to lift from this mantle to the surface or near surface. So, these are solidified volcanic system bands, these are the dikes, they are the fractures which are filled with magma and it is solidified. So, these are the dikes. So, this is representing layer 3 of this oceanic system. Here some field photographs, you can see this is the seated dikes, they are very closely spaced dikes and they are intruding into the basalt pillows at the upper part, and the lower part if you are moving down. So, this becomes coalitions and forming a shield type structure, that means very closely placed dikes are there. Then we are landing to oceanic layer 4, that is the gabbroic layer. So, layer 1 is sediment, layer 2 is pillows, layer 3 is seated dikes, then layer 4 is the gabbro. It is the chief layer of the oceanic crust and is characterized by its plutonic foundation. Now, it is the plutonic rock. So, gabbro, that is a plutonic rock, and gabbroic composition with few places of serpentinized ultramafic mineral. Now, here serpentinized. So, why serpentinized? Because we are allowing water to percolate down. So, this due to percolation of water, these ultramafic minerals they alter due to presence of water. So, finally, olivine and pyroxene, which are the chief component of this basalt, it is altered to serpentinite or serpentine. If you see here these black parts, they are fresh basalt. However, if you see some part becomes grey and whitish, they are nothing, they are the altered product of this basalt, they are the serpentinite or serpentine. So, that means part of this basalt it becomes serpentinized due to alteration, and this alteration in the presence of water, and this water comes from these fractures through these pore spaces from the pillow basalt. And this layer 4 or the gabbroic layer, which is divided into two layers again. So, this is called layered gabbro, the lower part it is called layered gabbro, and the upper part it is called isotopic gabbro. So, layered gabbro and isotopic gabbro, it names it says layered gabbro, that means it is a layer like material, and isotropic gabbro, that means it is isolated patches are there. So, if you see this field photographs of these two, layered gabbro, here you can identify and distinguish different layers, and isotopic gabbro, that means there is no layering occurs here. So, that is why these minerals, particularly the mafics, they are occurring within that dominated felsic as isolated patches. So, now the question arises, why this type of arrangement is there? Imagine there is a magma chamber inside and we are allowing the magma to cool down. So, the first mineral to crystallize the olivine, the chrome spinels like this. So, if you remember this Biomass reaction series, here we are creating olivine and then pyroxene, amphibole like this. Similarly, this side we are creating it is anorthite and here it is albite. So, that means I want to say when we have these minerals which crystallize, being their density is more, so they try to settle down to the bottom of this magma chamber. So, once they settle down, so they are forming layers. So, layer of rock is forming, layer of minerals which is mostly composed of ferromagnesian system, ferromagnesian minerals like olivine, pyroxene, they are settling down. Similarly, this is the plagioclase is forming at this similar temperature. So, it is also settled down. So, they are forming layers. So, now imagine once this from this magma, these components are removed due to crystallization. So, the remaining magma will be more felsic in composition. So, that is why those minerals which are forming that time, so they will try to settle down. However, that time this magma's viscosity would have increased because the mafic part we have removed and the temperature we have reduced and this magma becomes more felsic. That is why it will become more viscous compared to the initial composition of this magma. So, that is why these mafics which are crystallizing then, though they try to settle down, however, due to viscosity of this medium, high viscosity of this medium, they will not able to settle down. So, they will be remain here and there where it crystallizes. So, that means we are creating a rock which is mostly of felsic, but here we are having the mafics which are isolated occurring at isolated patches. That is why it is called isotopic gabbros. So, the lower part it is the layered gabbro and the upper part it becomes the isotopic gabbro. Here some of the field photographs are also given. This is the layered gabbro and these are the isotopic gabbros are there. The oceanic lithosphere forms at the mid-oceanic ridge and the widely accepted model proposed by Can, it describes hot asthenospheric material ascend buoyantly, sufficiently rapid up to a narrow zone to pass through the basalt melting curve and provides an interstitial melting of basaltic composition. Mostly if you imagine, we have a asthenosphere and we are just separating the two plates away from each other and we are creating a narrow zone, narrow rift environment, and through this rift environment the magma is moving up. This type of system it is called decompressional melting. So, decompressional melting is also it is called adiabatic melting. So, here we are removing two blocks away from each other, so that we are decreasing the pressure. Once we are decreasing the pressure, this it reaches the asthenospheric material, it reaches to the melting point. So, that is why it starts melting and creating the magma here, and the magma ascends through this fracture, it is forming the sheeted dikes here, and from this magma chamber we have these gabbros, layered gabbros and isotopic gabbros. Then we have this that is the sheeted dikes, then this magma is erupting here creating these pillows. So, this is a totally cross section that can be imagined from here. and the molten fraction increases in volume as the asthenosphere rises and eventually departs the parent material to ascend independently and produce the magma chamber within the lower part of the oceanic crust, that is layer 4. So, here we are creating a magma chamber which is separated from this rest of this asthenospheric system, because here in local we have reduced the pressure. So, we have decompressional melting we are creating in this region. So, we are creating a magma chamber here, and here this is the schematic diagram how the system is doing. Here we have a magma chamber, and this from this magma the mafic part first crystallizing and it settling down, crystal settle to the bottom of this magma chamber through non-viscous magma, because at the initial time when the temperature was high and the magmatic composition was that much, no differentiation or very little differentiation was there. So, this magma is of mafic composition and it is of less viscous. However, once more and more magma, more and more mineral is settled down, is differentiated, the magma becomes viscous. So, the first mineral to crystallize in the magma chamber is the olivine, and chrome spinel fall through this magma and form the basal layer of this dunite and peridotite, occasionally chrome spinel. So, this is the initial stage where we are creating the layered gabbros. With further cooling, pyroxene crystallizes and cumulates of a peridotitic layer. So, they are produced giving way upward to pyroxenite as the crystallization of pyroxene begins to dominate. So, gradually the olivine, the dunite is removed, then the rest number in the Bionc reaction series is olivine and pyroxene. So, after the removal of this olivine or the crystallization of the olivine, the pyroxene starts crystallizing because the temperature gradually drops. So, we are getting a layer of pyroxenite there. So, ultimately plagioclase this side is also crystallized and layered olivine gabbro is formed. So, much of this residual liquid still volumetrically quite large, then solidifies over a very small temperature range in the form the upper isotopic gabbro. So, that means we have this isotopic gabbro here, then we have layered gabbros here. A small volatile rich residuum is this differentiation process consisting eventually of a plagioclase and quartz is the last fraction to crystallize. Sometimes it is intruded at the base of this seated dike complex, and that is called plagiogranate. So, that means now imagine we have a magmatic system from which we first created the layered gabbro, then we created the isotopic gabbro, then we have this peridotite, dunite, pyroxenite, all these things, these mafic components gradually we removed, and the remaining magma become rich in volatiles, rich in felsic components. So, after all this crystallization, so that felsic part it creates the plagiogranate. Why it is plagiogranate? Because it is rich in plagioclase. So, that is why the name plagiogranate is here. So, this plagiogranate it intrudes into the seated dike complex. If you see here, this is the seated dike complex, they are the dikes and these are the plagiogranite part which is intruding at a tongue and apophysis, or it is a large scale body you can find here at the base of this seated dike complex. So, this is the complete topography or complete compositional system or compositional variation and lithological variation of a oceanic crust, starting from the sediment, then we have pilobasalt, then we have seated dikes, then we have isotopic gabbro, then we have layered gabbro, and all through later this plagiogranite is cross cutting. So, the plagiogranite being it is formed at the later part, but it is have intrusive relationship with some of these earlier formed litho units. So, plagiogranites are nothing, they are tonalite composed of quartz and sodic plagioclase with minor mafic silicate. So, these are nothing but the tonalite. Why it is non-tonalite? This is light tone, that is why it is called tonalite. So, light tone is due to the felsic components and it is mostly composed of sodic plagioclase, that is albite, and with minor mafic silicates. They typically have granophyric intergrowth and may be intrusive into layered gabbros, that we have seen here some of these plagiogranites. It is here some field photographs. This is the layered structure of this oceanic lithosphere, starting from the layer 1, which is sediment, then it is pillow basalt, then we have this sheeted dikes, then we have isotopic gabbro, then we have this layered gabbro, then it is cross cutting by the plagiogranite. Thank you very much.